Okay, so the work I present is joint work with Alex Summers, who's a great keynote you hopefully have seen this morning, all of you. Okay, so we're interested in modular static verification of imperative programs that, well, update shared state. And one of the challenges in this line of work is the well-known frame problem, which means that if we execute a statement, we want to clearly know which memory locations can be affected. Statement could be an assignment, but also a method call, asynchronous or synchronous one. When I say automated static verification, I mean the style of verification where we interact with the verification engine just by means of pre- and post conditions and invariants and maybe some ghost code. So other people call it semi-automated or auto-active verification, but this style of verification, just to be clear. So in order to deal with the frame problem, there's a well-known approach, namely permissions. If you know separation logic, just think of separation logic as the most well-known permission logic. To give you a brief idea of permissions, I'll quickly come to magic wands afterwards. So permission to a memory location means or denotes the exclusive access to that location. So in this small example, I have a caller, and the caller has the exclusive permissions to 2 memory locations, and it established some assumptions about those memory locations which are important for the correctness of the caller. And then the caller calls a callee, and the callee says I need to be able to write to one of those locations, so it takes over the permissions from the caller, and now it can do whatever it wants to that memory location. Since it's modular, we might not necessarily know what exactly the callee does. But the important bit is that the caller holds on to the other permission, and so it knows that the callee, whatever it does, it cannot change that, in here, blue memory location. And then the callee at some point terminates, and the permissions are transferred back to the caller, and maybe alongside some assumptions. And now the caller has the exclusive access to those 2 locations again. And in separation logic, a permission would be denoted by points to. X.f points to O, and in our logic and our syntax, we have an accessibility predicate, so this ACK of X.f denotes exclusive access to X.f, and then we can express logical properties such as X.f has the value 0. And if we have access to 2 locations, X.f and Y.f, then we know that X and Y have to be disjoint because we can't have the exclusive access twice. And that's similar to separation logic again. So this separating conjunction describes the current state in terms of disjoint substates. So for example, we can say that we have a binary tree in our current state, and that is composed of 2 disjoint halves, namely the left half of the tree and the right half of the tree. And this kind of reasoning is at the heart of separation logic-based verifiers because it allows us to do framing. We could say, well, there is a thread that can work on one half of the tree, and I keep the permissions to the other half of the tree, and therefore I know my assumptions about that half can't be violated in parallel. There's another connective which is called the magic wand, and it was introduced along the early work in separation logic, and it describes hypothetical states. And it can be interpreted, in particular if you think about permissions, as a promise. And the promise is that in any state, so that's hypothetical, if you provide permissions A, some set of permissions, then you will get permissions B. So that's the promise. And a couple of years ago, there was a verification challenge at the Verify This verification competition. And the scenario was to iteratively traverse a recursively defined tree. Well, let's stick with our binary tree here. And then the challenge there is that you have a loop, and you need a loop invariant in our line of work, and the loop invariant has to describe a partial data structure, namely the partial data structure that you either visited on your path down through the tree, or essentially the left or right subtree you ignored. So in this image, the partial data structure is the gray part, and you're traversing the tree down, and you want to modify this golden subpart. And that's a problem that comes up in functional programming as well, and there are data structures like zippers, for example, that try to deal with this problem. So with the magic wand, we can implicitly describe this partial data structure as a promise. And the promise is, if you give up the golden subtree, then you will get back the complete tree, and the golden subtree has been plugged in. So the implicitly described data structure here is the gray part of the tree, where the triangle at the bottom is missing. And then there's a modus ponens-like rule which allows us to make this promise applicable. So that says, if you happen to have the subtree that's missing and you have this promise, then you can exchange both, in terms of permissions again, for the whole data structure. So you actually get what the promise tells you. But you have to give up some subpart of that, and the promise as well. And this can be derived from the semantics. So here are the formal semantics of the want, and the important bit is this quantifier, because they say that a current state satisfies a promise A magic want B if for all states where A is satisfied, where what you give up is to be satisfied, then the combination satisfies B. So that's the part you're promised. And this magic want connective has been proven to be useful in pen and paper proofs about data structure, so these partial data structures, for example, or usage protocols like iterators, but also other non-data structure related proofs, for example, about synchronization barriers. It's typically not supported in automated verifiers, though, and the reason is this quantifier over the states. That's difficult to handle by automated tools. The only exception we are aware of, besides our tool, is Vercors, which is being developed in the University of Twente, and they essentially developed support in parallel, but their support technically differs significantly from ours. So now we want to automate reasoning about magic wand formulas. And entailment for magic wand formulas is undecidable, and what we want here to make this to control it a bit at least, is we need some kind of lightweight user guidance to direct the verifier. And you've already essentially seen all the ingredients that we need. We need a point where we make such a promise, and then we pass this promise around between different methods or different threads, and then at some point we want to use the promise. And the ghost operations that you need in our methodology is a package. So packaging a want means you create this promise, okay, and there's something to check since we have to make sure that the promise is sound. And then transferring the promise around, we treat this magic wand promise as an opaque resource, which means that the verifier doesn't try to reason with its semantics until it's explicitly told so, and the verifier is told so by an apply statement. So that means we want to use the promise at that point. And that's essentially applying the modus ponens rule I have shown you earlier. Okay, so the challenge here is clearly the package statement, because we have to make sure that applying the promise in some future state is actually sound. This is a bit trickier than it might sound. So what we do at this point is there's a concept called footprints for magic wand formulas, and the footprint of a magic wand is a set of permissions that guarantee that this promise is actually sound. So that guarantee that at some future point, giving up A and the promise A magic wand B and obtaining B at that point is actually sound. And we do that by carving out in our example, partial data structure that's implicitly described by the wand. We take that away from the current state, so we make sure nobody can modify it in the meantime until the promise is applied, and that makes the promise sound. So that part of the data structure is effectively immutable, and at some point you plug in the golden triangle here, so the substructure you can modify, and then you get back the whole structure. The question is, this footprint could be the left triangle, so the tree with the hole, but it would also be sound to choose the whole data structure. Clearly, then nobody can violate the promise in the meantime, but of course you can't do what you wanted to do in the first place, namely modify the sub-data structure. Or in general, we could just take all of the permissions we have, put them into, so take them away, put them into the wand, if you will. That would be sound, but that wouldn't really be useful, because then the verification will shortly afterwards fail, since we don't have any permissions anymore. So the question is how to choose a footprint. One way of doing that is to let the user choose and specify a footprint, but that clearly incurs some annotation overhead. So it would be better to automatically compute the footprint. And we want the computation to give us a minimal footprint. So in this example, the one with the hole, so the left structure. And the computation should be understandable by the user, so the user shouldn't be surprised by the outcome, and the user should kind of know which footprint will be picked. So the algorithm we devised works as follows. Say we want to package a magic wand formula A, magic wand B, where B consists of individual conjuncts B1 to Bn. If you want to know more about the language that we support in the tool, just ask me afterwards. we start in some given current state. So in that state, we hold permissions to certain memory locations, and we know that those have certain symbolic values. And then we set up a left-hand side state that satisfies A in our formula. And again, A might talk about permissions, then we'll have some permissions in that state, and A might also talk about symbolic values. So for example, W1 might be some positive integer, so we have some assumptions there as well. And we also create an empty right-hand side state, and that will be populated as the algorithm goes along. So we iterate over our conjuncts on the right-hand side, over these BIs, and then there are two options. So BI could be an accessibility predicate, so it could mean I need permissions to some location x.f, and then we transfer these permissions, and we transfer them preferable from the left-hand side state, so that's the hypothetical state in which this promise eventually will be applied. We take them from there. If we don't find them there, we'll take them from the current state, so that means these locations will be immutable, they will be part of our footprint. And if we can't find them in either or, then package fails and we have a verification failure. These permissions will be moved to the right-hand side state, and assumptions that we have, so in the simplest case, if we know certain symbolic values, these assumptions will be transferred as well. The other option here is that BI is a logical property, so for example, that a memory location x.f has the value 0. And in this case, we'll check this logical property in the right-hand side state. Okay, let me give you some examples. So if we want to package the trivial one that says if you give up permissions to x.f, you'll get back permissions to x.f, then, and we assume that we start in a current state where we have these permissions, then we'll create a left-hand side state that satisfies that we have permissions to x.f, and then we'll populate the right-hand side state. So in our case, we only have one conjunct on the right, namely access to x.f. We'll take the permissions from the left-hand side state. That's good. So package succeeded, and we can continue verification. Now we have this promise, and if we want to use it, we'd have to give up the permissions that we still have in our current state, which is possible. They are still there, so that's all good. If we change the one to say you don't have to give up anything, but in return you will get permissions to x.f, then we'll set up an empty left-hand side state. Satisfies true, okay, easy. But now we have to take permissions from the current state, otherwise the promise wouldn't be justified. And that succeeds, we gave them away, now x.f is immutable, and the promise is sound, a package succeeds, and we can continue the verification. If we change that to strengthen the right-hand side state, so now we say you don't have to give up anything, but you'll get permissions to x.f, and x.f will have the value 0, so that sounds fishy, but if we assume that we start in a current state where we have the permissions and x.f actually has the value 0, then it's okay, we can transfer both the permissions and the assumptions to our right-hand side state. So now x.f is immutable, nobody can change the value of x.f, so the promise is sound. When we apply it, we get the permissions, the value will still be 0 at that location, it's all good. Package succeeds, and we can continue. If we change the example to say, if you give up permissions to x.f in any state, so now on the left-hand side, there is no constraint on the location, and the promise is you'll get back permissions and the value is 0, that shouldn't work. What we do here is we still have a current state where we have permissions to x.f and where x.f has the value 0, but we'll create a left-hand side state that satisfies the left-hand side, so we know we have permissions there, but it has some unknown symbolic value. And those permissions and this unknown value will now be transferred into the right-hand side state, and we'll check the second conjunct, namely that x.f is 0 in the right-hand side state. That will fail as expected, so that's a verification failure, and package didn't succeed, and it shouldn't succeed because that would be unsound. So these examples, these were trivial ones. I'll show you a more interesting example a bit later. In our verification methodology, we also have other features. So for example, abstract predicates. This is a fairly well-known concept from separation logic. It's used to describe recursive data structures. So we stay in the context of trees, and a tree predicate could say that there is in that case, the empty tree essentially, at x if x is equal to null, or if x has 2 pointers, left and right, and there are subtrees at the left and at the right pointer, then you also have a valid tree at x itself. For the rest of the talk, I'll ignore the null case, but of course it's supported in the tool. So let's stick with this, the valid tree case, essentially. So for dealing with recursive data structures, we have some ghost operations already, and this is fairly standard. Other separation logic-based tools have that as well. These are called fold, unfold in our tool, and in others they are, for example, called close or open. Folding essentially takes the two halves and gives you a proper tree at X, and unfolding is the reverse. If you have a tree at X, you unfold it, and then you get back the two halves. So these are ghost operations that already exist, and we of course have to integrate them into our magic wand handling. Here's an example. If I want to package a wand that says you give up the left-hand side, so you give up half of the tree, and you promise to get back the full tree, then with the handling of predicates that I just showed, it's clear that we have to do a bit more. We have to say you give up the left tree, and then you fold those two halves, and then you have the property. So there's a promise, but there's also some necessary ghost code that we have to be able to integrate into the package statement. If we go back to the algorithm, and we assume that we are in a state where we have both those halves, and now we create a left-hand side state in which we have the permissions to one of the halves, so in this one, the golden one. And now we transfer the left subtree from our left-hand side state, and the right subtree from our right-hand side state. Sorry that wasn't animated, but I couldn't convince PowerPoint to do the animation properly. So now our right-hand side state has the promised full tree, so that's all good. And we are still left with the half of the tree that we have in our current set. Oops, and I think there's a, yeah, okay, sorry, the left-hand side state should now be empty, my bad. So the important bit here is that this fold operation has to interact with our package operation. And the same, of course, holds for unfold. And if the logic is more complicated, maybe it needs more ghost statements, and they have to be integrated into package and apply as well. And this is just an example that that's possible in general. So we have an implementation. It's part of our Viper verification infrastructure, which Alex mentioned this morning in his keynote already. It's based on symbolic execution. And we have a fairly rich logic. It supports unrestricted abstract predicates, abstraction functions, or pure functions in JML. We have quantifiers, mathematical sets, sequences. You can specify custom mathematical domains, for example, pairs or type relations. And we have a fairly flexible permission model as well. So you can do parallel readers and not only exclusive read or write access, as I used in my initial example. We have a set of interesting examples. They all verify in between 1.6 and 3 seconds, so that looks pretty good. And the verification challenge from 2012 is, of course, part of that. So it verifies in 3 seconds. I'll show you the code in a minute. I mentioned Vercors earlier, and they also encoded this example in their tool, and it takes about, well, it took about 6 minutes. They originally used Chalice and Boogie as the verification backends. In the meantime, they switched to our Viper backend, and now it takes them 60 seconds. So that's pretty good. They don't use our native support for magic wands. They have a clever encoding that worked in Chalice and Boogie already, and they keep it, and that's probably why it still takes them a bit longer. All right, we also have simple error-driven inference heuristics that are able to infer all of the package and apply statements that we use in our examples. The verification time increases by at most half a second, so that's all right. Coming back to this verification example, the challenge from 2012. So I said we need this loop invariant that describes the partial data structure, and as I just argued, we'll use a magic wand for that. I'll show you a bit of code in a minute, and there will be two symbols A and B, just as I used them in my talk right now. So A will represent the bit of the tree, the binary tree that we are still modifying or will still have to traverse. B, so that's A. B will be the whole data structure, so the binary tree with the rest plugged in eventually when we use the promise. And the magic wand, A, magic wand B, will denote this promise that at some point you can plug in A and you'll get back the whole data structure B out of that. So this is how the code looks. You're, of course, not supposed to read it. It's just to give you an overview of how much code there is. The important bit is the highlighted lines here are the ones that are related to our magic wand support. So the rest is functional properties, spatial properties, the usual separation logic bit, invariants, pre and post conditions. So the yellow parts here are named macros. very simple. It's just to make it writing a bit convenient. Our language is not meant to be written by hand in general. It's like Boogie. You're supposed to generate it automatically, but we want to make it sort of reasonable for demos. So we have these named macros. Anyway, they can be inlined, so those two lines could go. The green line is what you need in any case, because that's the invariant, and we need the invariant. And the orange bit, that's inferred by our heuristics. And I'll show that when I show the tool. So in essence, you only need the invariant, so the green part, and if you want the invariant to syntactically be a bit shorter, as it is here, then you'll probably also want the named macros. Otherwise, just inline them. Okay, so this is, hope that's readable. So this is our implementation, and you can see the colors again here. So this is the named macro, and then is it at the beginning of the method. This is the tree delete example. Forgot to say that. So the task was to delete the minimum example of a sorted binary tree, so essentially the leftmost element. We ignore the case where there is no left element. So the important bit is this code here. So that's the loop. And then what happens here is that before the loop, we establish the promise. Right? We have to establish the loop invariant. And here's the loop invariant that says, well, I have this promise, and at any point, if you give back the subtree, you're still iterating over your promise to get back the whole tree. That's the important thing with the modified subtree plugged in. And then at the end, so what we do is we unfold, so that means we go one level down in the tree, and then at the end here, we update the promise. So we traverse the data structure. So the golden triangle that I used on my slide is essentially shrinking and shrinking as we traverse down the tree, and eventually we find the leftmost element. But while we're going around the loop, we have to update this promise, essentially saying the thing you plug in at some point gets smaller and smaller, but you promise to get the big whole tree out of it. So conceptually, we have to transfer some permissions which we currently have in our current state into this footprint, so essentially into the promise. Okay, and then at the end, after the loop, we apply the want, and that's necessary because we want to establish the post condition of the method. So let me run this. Okay, runs quickly, and we have no errors. That's good. So now I want to remove all of the orange bits. So I commented them out here, and you see the invariant is still there, and further up, currently can't see that, but the named ones, the named macros are also still there because we still use A and B. But the other package and here the apply statement has gone. So if we try to verify this, then it fails. Okay, sure, because the heuristics are switched off. So I'll switch them on, and that's a bit hacky. I'll just declare this field here to switch them on. But if I run it now, then it verifies again. Okay, and time is reasonable. So if you have questions about the example, this was just a quick run through, just ask me afterwards. Okay, so the tools are open source. Just go to our website and download them. They are hosted on Bitbucket, but there's our research overview page. So what I presented in this talk was a novel algorithm for computing Magic Wand footprints. As far as we know, it's the first automatic footprint calculation algorithm. It's sound. We have a proof sketch in our paper. It's permissive, by which I mean it tries to find the smallest footprint. It tries that because under the hood we talk to SMT solvers, and of course they can't always guarantee an answer, so it might not always be the smallest one, but in practice it works quite well. It's predictable. We formalized the implementation and the algorithm, we formalized the algorithm verifier independently. So I said it's implemented in symbolic execution, but we only assume a very limited set of basic operations that the verification state that's represented in the verifier has to allow. So we're optimistic that it can be implemented in non-symbolic execution-based techniques as well. So we're the co-first together with WhereCourse that support magic wands in an automatic verifier. You've seen that the annotations that the user has to provide are fairly lightweight. We have convincing initial results in terms of expressiveness and performance. And we are optimistic that having magic wands in automatic verifier allows more people to use them in their automated proofs and maybe also to explore new ways of using magic wands in their proofs. Thank you, and please ask questions.
Thank you for a wonderful talk on a very, very subtle matter.
Thank you.
I wanted to ask some more about these restrictions that come from the fact that you need to calculate the footprints. Two questions.
Mm-hmm.
One, it seems to me that you are imposing some restrictions on what can happen, what can appear on the left-hand side of the magic wand. And I have seen some restrictions that such restrictions applied to tools in general in the magic wand. So I wanted to ask whether you can classify those restrictions.
Okay, so so there's a technical restriction, namely that you can only talk about a location if you have permissions to that location. And that's a concept called self-framing in the logic we're using. So separation logic formulas per se are self-framing. So if you think in separation logic, that's not really a restriction. Otherwise, you can mention arbitrary things on the left-hand side. So you can make...
You forbid on the left-hand side but to have access...
okay. No. So if you use pure implication, then that's true. So it's essentially the framework or the subset of separation logic that Smallfoot introduced a couple of years ago. And if you have a regular implication, then the left-hand side has to be pure in the sense that there are no permissions allowed. With Magic Wand support that we have, that's not the case. These A's and B's can essentially be any assertion that you can write down in our logic, and they can have permissions. And I mean, essentially, they must have permissions. If your Magic Wand promise wants to promise anything interesting on the right-hand side, so for example, as in this example, you will have to put permissions on the left-hand side. So that's definitely not a restriction. You can have Magic Wands on the left-hand side as well. You can have predicates. No.
Okay, so that I misunderstood then. The next question is, you said that because you are using theorem provers in order to prove implications, you might not be able to calculate the minimal footprints. Do you have the certainty that you always can calculate a footprint?
If the package operation is okay, that's a. So we don't have a proof for that. I think that if you have the sufficiently many permissions in your current state, then the algorithm will take as much as it thinks it's needed to ensure soundness. And if it can take them from the current state, then it's all good. As I said earlier, this footprint, depending on how strong the underlying theorem prover is, might be a bit too big. And you said there might be implications on the right, and that's true. There can be conditionals on the right. And if we don't know the value of the guard of that conditional, then of course the algorithm has to be conservative and take, say, all of the permissions from the then and the else branch. But then if you learn something about the conditional afterwards, you'll also learn that you haven't actually taken those permissions away. So if there's a conditional on the right that says some Boolean, and if it's true, then take permissions to x.f and otherwise take them to x.g, and you package the one, then until you learn more about B, both permissions will be out of your reach. But if you then branch on B, and you know, okay, now it's true, then you know that you actually haven't given away the permissions that are required in the else branch. So it's true that in certain situations the footprint might be larger than you would hope for. But as soon as you learn a bit more about the state, then this at least resolves. We haven't, in our examples, we haven't seen an example where you kind of take, or where too many permissions are taken away from you, and you should at that point already know that that's not necessary. So we have really only seen an example where you just hadn't enough knowledge, then more permissions were taken away, but as soon as you gained the knowledge, you noticed, I haven't actually taken those away.